Hi there, Mr. Sutton here, bringing you the Pre-Cal Honors 2-7 Extra Practice Solutions on applications of polynomials. On this problem, we have a box with no top built by taking a 5x13 sheet of cardboard, cutting out some squares from each corner, and folding up the sides. So this is kind of a visual of what's going on. We've got this rectangular piece of cardboard, and we cut out the corners and then fold up each side to form a box. We want the dimensions of the square that are going to yield the maximum volume. So by dimensions of the square, we're basically asking for like the side of the square here. Since that's really the only thing we can control on this problem, we're going to call that side of each square x. So it's the same x all the way around here. So in order to maximize the volume, we actually need to come up with a formula for volume, which means we're going to need to know a little bit about the length, the width, and the height of this box that we're forming. So it would help if we knew the length of this side here after we cut out these squares and fold up the side, and also the length of this other side. So this side right here, since in general we have a 5x13 sheet, we're assuming this shorter looking side is our let's see, it looks like this is going to be 5 inches, our 5-inch side here. If we have 5 inches to play with and we've already cut out an x over here and an x over here, then that leaves us with 5 minus 2x for the length of the side once we actually fold that up. By the same token over here, this was initially 13 inches altogether, but we take away 2x from that. So we've got 13 minus 2x for this side. So in general, the volume of a rectangular prism, a box, is going to be length times width times height. So our length we can represent with this 5 minus 2x. The width can be this 13 minus 2x. And the height, once we fold these sides up, will be the length of the side of this actual square here. That actually is the height of the box. So we have one thing times another thing for our volume formula. Now, once I've got this, I want to put this in my Fmax function on my calculator, but to do that, I need to give it a range of values, which means I need to know basically the domain of this function, the places between which my total volume is 0. So let me figure out what values of x zero out this box. So for our first parentheses, if I subtract 5, divide by -2, we've got 2.5 for that first root there. For the next root, this is going to be, let's see, 6.5. 2 times 6.5 would give me a 13 to zero that out. And our last root is going to be just 0. If I plug in 0 for x, that also will give my box a dimension of 0. So at 2.5 then, that's, other than 0, that's the place where we run into trouble with this box. At 2.5 inches, we've used up this entire side, and we no longer have a length for these boxes. So if I'm going to successfully build a box, I can only use x values that are between 0 and 2.5. So those are my domains, 0, 2.5, x between those. At this point, I'm going to go ahead on my calculator, and I'm going to use my Fmax function. I'm going to put this volume function in my y1, and I'm going to use Fmax, and this is the setup on my calculator. I use y1, comma x, and then my two domain values, 0 and 2.5. Let's do that on the calculator now. So on my calculator, I went into y equals, and I just put this volume function in my y1, just so it's easier to refer back to. Let me quit out of there. Quit. There we go. And now I'm going to go to Math 7 for Fmax, Math 7. And let's see here. We'll do alpha trace, pulls up my y menu. Let's pick y1 out of that, comma, we always put x as the next thing, and then 0 and 2.5 go in there as well, giving me a grand total of, this is about 1.107. So I'll round that off to 1.11, and that's in inches. That's going to be the length of our squares that maximizes our volume. They didn't ask for the actual volume, so we're going to quit while we're ahead. For this problem, we're making an open box by taking a square piece of cardboard, 12 by 12, and cutting squares from the 4 corners, and then folding up the sides. We want to find the dimensions of the square that maximizes the volume. So at some point I'm going to have to write a volume formula But to do that, I want to get everything in terms of x, in terms of the length of this square here. So for that, I'm going to need dimensions of the other sides, because my volume formula is going to be length times width times height. So for each of these sides, since they're each 12 inches, and I'm taking an x here and I'm snipping another x here out of each side, I'm going to end up with 12 minus 2x for the length of each of these sides. And now to build my volume formula out of all those x's, I've got, in general, length times width times height. So that's going to be 12 minus 2x times another 12 minus 2x. So we could say 12 minus 2x squared. All of that times an x. So this is the function I'm actually going to try to maximize on my calculator. Now to do that, I'm going to need to figure out what range of x values to look between for the max on the calculator. Because by itself, this function is a polynomial and goes forever in both directions. So we have to give it some parameters here. So I'm going to look for the x values within which this function actually makes sense. If I plug in 0 for x, I have no height and I can't build a box. What number could I plug in to get rid of the other dimensions as well? That's what I need to look at here. So I'm going to find the roots. We've got a root at 0, and also 12 minus 2 times 6 would zero out this function. If I have a 6-inch side here, or actually if my squares are each 6 inches, then that's going to leave me no length or width on this one. So my x values have to stay between 0 and 6 for this function to actually build a box and make any sense. So my domain then, we're going from 0 to 6, and I'm going to use my fmax function on my calculator. In a sec, I'm going to plug in my volume for y1, and I always have to put x as the next thing in my fmax function that I do here. And then the next two numbers are the x values that I have to stay between, my domain. So let me go ahead and plug all that in. So first things first, I went to y1, y equals, and I put my volume formula in as y1 just to have it in a nice concise place. Next, let me quit out of here, and we'll do math 7 to pull up fmax. Let me do alpha trace, and that'll bring up my menu where I can pick y1 out of that mess. We'll do a comma, an x, a comma, and then my two numbers, 0 and 6, that I have to plug in as well. Press enter, and the ideal square length is 1.99999, which we will just kindly round off to 2 inches. For this problem, we have an open box made from a 3 by 8 foot rectangular piece of sheet metal, cutting out squares of equal size from the four corners. So here's a visual of what's going on. We've got this rectangular piece of sheet metal, squares being cut out of the four corners, and then we're bending up the sides to form a box. We want to find the maximum volume that said box can have. So to do this, we need to write a volume formula, and then we'll use our calculator to find the max of it. Before we can find a volume formula, we need to express everything in terms of one variable so that we can actually use the calculator for it. So I'm going to let x be the length of one of these square sides here, because that's what we have the most control over if you're cutting into this metal. And then that means that we have two other dimensions we can talk about. So when we fold up this box, these x's here, those are going to be the height of the box. But what's going to be the length of the box, or the width of the box? Well, let's say that this side right here up top is 3 feet. I mean, it doesn't really matter, but visually it looks like this is going to be the 3 feet, and this is going to be the 8 feet. So if I have 3 feet initially, and I cut out two squares of x length each, this dimension here is going to be 3 minus those two x's that I just cut out. And then this dimension here is going to be the 8 feet minus the two x's, again, that I'm cutting out from that side. So now for a volume formula, in general, we know volume of a rectangular prism, a box, is length times width times height. So plugging in what we have here, we can write 3 minus 2x times 8 minus 2x times that height of x that we were talking about. So this is the formula we're going to try to maximize on the calculator. Before we can do that, though, we need to figure out the domain, the permissible x values, so that our calculator knows where to look. So for those, I'm going to first figure out the roots of this equation, the places where this is zeroed out, because we obviously don't want a box with zero volume. So if I can figure out the x values that I don't want to go past, that will help me out here. So going from one end to the other, this first parentheses, I'm going to get zeroed out if x is 1.5. And then for the next one, if x is 4, we get zeroed out. And then 0 would make this x 0, which would make everything 0. So the domain, the smallest we can have is 0 for these sides here, because that would give me a height of 0. And if I go up to 1.5, I'm going to lose this entire side here if I have two x squares that are 1.5 in length. So that's kind of my limitation there. If I go past 1.5, I mean, I might start losing this side over here, but it doesn't really matter because by then I've got a negative side right here. So we've got a domain then between 0 and the lesser of those other two, 1.5. At this point, I'm going to plug this into the calculator. I'm going to use fmax, and the format of this that I'll show you in a sec is going to be the function here, which I'm going to enter as y1, x, which is just literally x. I write that on the calculator. And then my two domain numbers, 0 and 1.5. Let's go to the calculator now. So I'm here in my y equals. There's the y equals button right there. And I've entered this whole thing in y1. Now I'm going to quit out of there. And I'm going to go to math 7 to get fmax. I'll do alpha trace, and I'll press enter on the y1 because that's where I entered my function. We'll do a comma and an x, comma, and then 0 and 1.5 because that's what we have for our domain here. And close the parentheses if you want. That gives us about 0.67 if we round that off. So that's the x values that's going to maximize the volume. But that's not the actual max. To get the maximum, we have to go back to the calculator and actually plug this number into our function. Since I stored my function in y1, I'm going to go back to alpha trace and click on y1, and then I'll open a parentheses, and I'll just push up arrow and press enter to yank that and put it in there. You could also do second this thing here to get answer, and that would also put your last input in there. Pressing enter, we get about 7.41 if we round that off, and that's going to be in cubic feet. On this problem, we're going to make an open rectangular box from an 8 by 15 inch piece of cardboard by cutting out squares from the corners and folding up the sides, kind of like they're showing in this picture here. We want to find the max volume that this box can have. So I need to get a volume formula and then maximize it. In general, volume's length times width times height for a box, but I want to get everything in terms of just one variable, and this picture kind of gives me that variable. If I make x the length of these squares that I'm cutting out, I can use that to define all the other dimensions of my box. So just taking a look at the other dimensions here, we have a height is what this x is going to give us, but now we also have the length and the width of this box. The length of the box, though, is not this whole 8 inches, because if you look here, we've cut out two of these x squares from this 8 side. So that's actually going to be 8 minus 2x for that side. And then for this 15 side here, again, we're losing 2x out of that total distance, however too much 2x is. So we're going to have 15 minus 2x there. So writing out my volume formula, length times width times height, I can write 15 minus 2x times 8 minus 2x. That's the length and the width. And it doesn't really matter which one is which. And we have a height of x. Next, before I can actually use my calculator, I need to figure out the domain of this function because I have to tell my calculator which x values to look between for the max. So what's the lowest x value I can have? And what's the highest one I can have? To figure this out, I'm going to figure out what x values zero out this function. Because at some point we're going to run out of height if x is too low, and if x is too big, at some point we're going to run out of one of these other sides. So getting the roots of this equation, for my first parentheses here, if I add 2x and divide by 2, I've got 7.5 for that first root. The next parentheses get zeroed out if x equals 4, and then 0 for x zeroes out everything because of this lone x over here. So if x is 0, I've got no height, so I can't go below 0. And if x grows to 4, then those two 4x squares there are going to get rid of this entire side over here that used to be 8. So I don't want to go bigger than 4. I don't want to be exactly 4 either. So my domain then is the smaller of these two. It's going to be from 0 to 4 for my x values. To get something on my calculator now, I'm going to go to fmax, the fmax function, which I'll show you in a sec. And I'm going to plug in my function itself, which I'm going to store as y1 because I'm going to use it more than once. I'm going to just write x, and then I'll put my domain in there as well. So let me show you this on the calculator. So here I am on the calculator. I went to y equals, and I entered my function here under the y1, which I entered the whole thing, and I didn't forget that little x at the end either because that's important. Now I'm going to quit out of that, and I'm going to go to math, and I want 7 fmax. I'm going to put my function in there by doing alpha trace, and then y1 is already selected, so I'm going to press enter to put that stored function. Then we have a parentheses, or actually a comma, then an x, comma, and then I'm going to put my domain numbers, 0 and 4. Let me go back to the calculator for that. 0 and 4. When I do that, my calculator gives me a value of about 1.67, and that's going to be in inches. So that is the x value, that's the square length that maximizes the volume. To find the actual maximum itself, I have to take this number, and I'll take the exact value and plug it back into this volume function for x. So going back to my calculator, I'm going to do alpha, trace, and y1. And now I'm going to open a parentheses, and I'm going to put this answer that I just got into there. A quick way to do that is just do second negative sign there, answer, and then press enter, and that's about 90.74, and that's going to be in cubic inches. For this one, we have an open box being made from a 20 by 60 inch rectangular piece of sheet metal, cutting out congruent squares from 4 corners, folding up the sides. Here's a visual. There's my 4 squares I'm cutting out, and I fold up the sides of this thing to make a box. We want the maximum volume of that box. So to do that, we need a volume formula. We need the domain of that volume formula, and then we need to use the calculator on all that stuff to get the volume. So let me start by getting a formula. It would help if I could express everything in terms of one variable. So a volume formula, we need a length, a width, and a height to talk about. The one that we can have the most control over is the height of this box. That's going to be the length of these squares that we're cutting out. So I'm going to make that my x, and I'm going to base everything off of how big those squares are on one side. So I also need a length and a width. The length is going to be whatever this side is when I fold it up. Initially there were 20 inches here, but now I've lost an x out of each side of that 20. So now that's going to be down to 20 minus 2x, whatever x is. And I initially had 60 inches over here on this side, but again I've lost 2x from those squares, so I've got 60 minus 2x. My volume formula then, length, width, height, is going to be 20 minus 2x times 60 minus 2x times the x over here. Just these 3 dimensions multiplied together. And I need to get the domain for this thing to figure out the acceptable x values because my calculator needs to know where to look for the max, where to look for the answer. So my domain is just going to be the x values where one of these dimensions gets zeroed out. So I'm going to find the roots of my formula here, and then that'll help me get the domain. So going from left to right, zeroing out each of these parentheses. For this first one, a value of x equals 10, we'll zero that one out. Let me put 10 in there. There we go, that's better. And then for the next parentheses, if I add 2x and divide by 2 after setting this equal to 0, I've got x equals 30, and then finally x equals 0 for that last x. So for my domain, x can't be 0 or less than that because then we would have a height that's either non-existent or negative, and we wouldn't have a box. We can't also have something that's 10 or bigger because once I get to 10, I've used up this entire length side up here because I've got 20 minus 20 basically. And then it doesn't matter if we go past 10 because we've already used up this side. So my domain is going to be from 0 to 10 then. On my calculator, I'm going to use my fmax function that I'll show you in a bit. And we're going to do fmax of y1, which is where I'm going to store this volume function in a moment. And then we have a comma x, and then our domain 0 and 10. let me show you that on the calculator. So I'm here in my y equals. Here is the y equals button. I entered my function in there. And then let me move that over so we can see. I'm going to quit out. And I'm going to do math 7 for fmax. I'll do alpha trace to pull up my y1 function there that I've stored my volume in. And then I'll do a comma, x, comma, and then my domain 0 and 10. And that gives me roughly 4.51. That's going to be inches. Now that is not the volume. That is the x value at which we maximize the volume. This is the length of the squares that maximizes the volume. But we need the volume itself. So we need the output from the volume function when we plug this x value in. Going back to the calculator to do that, I'm going to go to alpha trace and pull up y1 again, because that is my volume function. And if I open a parentheses, and let me just do second, and then this little minus to get answer, and put that in there. So basically the value we just came up with, plugging that in, we get about 2,524.52, and that'll be in cubic inches. That's the maximum volume this box can hold.